In the last class, we were discussing about the interferences in hydride generation atomic absorption spectrometry. So, what we said that there are virtually no spectral interferences in the determination of mercury. So, basically because we measure the atomic absorption of mercury only around 253 nanometers or something like that, and then there are not many spectral interferences are known, because most of the spectral interferences have already been tabulated and available in the databases all over the world. So, what we have to understand is whenever you want to determine mercury, there are no spectral interferences, and systematic errors occur to a large extent owing to the blank values, because mercury contamination is almost everywhere in the whole world. Even the air we breathe contains some amount of mercury, and the laboratories definitely yes, and then coal burning definitely yes, automobiles not much, but any air, cities, urban areas do have lot of mercury in the air which we normally breathe. So, the systematic errors always occur to a large extent owing to the blank value itself having some certain amount of mercury. So, apart from that, we have laboratory glassware, losses due to volatilization, adsorption or chemical reactions also can occur. So, in the extreme cases, this phenomena can lead to substantial errors. Basically, any environment, normally atomic absorption instruments are not kept in AC rooms, they are kept in the open atmosphere, and sometimes air itself can be contaminated. There may be volatilization of the mercury from previous experiments in the laboratory, etc. So, in extreme cases this can lead to substantial errors, that is the statement we want to make. So, in non-contaminated areas, regions in the atmosphere, the concentration of mercury is there, but it rarely exceeds a few nanograms per cubic meter. That we have to understand. That means, if the concentration of mercury is less than few nanograms per cubic meter in the air we breathe, we can call it as non-contaminated area. But in the laboratory atmosphere, values of even 100 nanograms per meter cube are not uncommon. That is 100 ppm, 100 ppb are not uncommon at all in the laboratory atmosphere. Okay. So, what are the typical sources of errors? Normally 99% of the cases, whenever we have to handle mercury, the storage of the sample plays a very important role. The soils, for example, if you want to analyze soil, there is a certain amount of mercury contamination can occur from anywhere, and then glassware definitely yes, okay, because quite often we keep the mercury in the glassware, handle them, etc. And then suppose there is mercury in a plastic foil, in a bag, plastic bag, then again there is a diffusion of mercury because of the possibility of vapor pressure. I have already told you that mercury has got a very high vapor pressure, 0.0031 atmospheres at room temperature. So, whatever is the air containing mercury, if it is in a plastic bag, can diffuse outside from the plastic bag itself. So, we have to be very careful regarding the diffusion of mercury through the plastic foils. And then adsorption of mercury onto the glass walls, definitely yes, of the containers. And then contamination of the reagents. If you are determining mercury day in and day out in a given laboratory, then there is a possibility that contamination of the reagents and acids occur quite often. It is the experience of all the people who work on mercury for long periods. So, the reagent itself, if it gets contaminated, definitely you will get very high blank value. So, obviously blank value will be subtracted in the final estimation, but still there will be contamination, and we have to be very careful how we keep our reagent and acids. That is also very important. Most of our acids need to be free from mercury. So, during sampling, digestion, storage or actual measurement also contamination can occur. Yes. Then precipitation of mercury on noble metal surfaces. Whenever you have platinum or something like that in the laboratory or elsewhere, mercury can form an amalgam, and mercury vapor can get deposited, form an amalgam, or if it comes in contact with mercury salts, then the mercury can get reduced on the noble metal surfaces and get contaminated. So, that is another source of error we normally recognize on metal surfaces. So, then what else? The chemical exchange reactions. For example, if you are passing mercury vapor or the sample through a rubber tube or a PVC tube, the PVC and rubber itself may be having certain amount of contamination, or mercury can get exchanged from rubber to the air or air to the rubber tubing or PVC tubing. And then sometimes we find that calcium chloride is also an unsuitable drying agent. It may have impurity of mercury leading to high blank values. So, the other one is magnesium perchlorate. That is a better drying agent, and what we want to say from this slide is these are the different kinds of contamination, possible contaminations in the normal determination of mercury at parts per billion level. You please remember that only when we determine mercury, we go to parts per billion and parts per trillion level, and cold vapor mercury is the best method to determine mercury in ppb levels. But whenever you are doing estimation in parts per billion level, you have to be very careful with respect to the contamination. So, if there is contamination from the sample, you can change the sample. If there is acid, you can change the acid. If it is plastic foil, you can change them. But during sampling, digestion, storage and actual measurement, they are not under your control. So, one has to be very careful with respect to blank values in this, and then we have to make sure that noble metals are not around, exposed into the atmosphere, and then rubber tubing, if it gets contaminated, you have to change it, and calcium chloride, if it is not convenient and if it gives you blank values, you should be able to change it to magnesium perchlorate. So, what are the other interferences of in the determination of mercury? We did say that it is almost specific, but there is a certain possibility of interference from some other source, that is non-specific absorption, and these I have tabulated them here, and by both methods. And then for example, if there is silver along with SnCl2, it may interfere in the reduction of mercury to elemental state. So, this kind of interferences can occur. It is not the atomic absorption measurement, but it is the interference which will reduce the conversion of mercury salt into mercury element in the solution, because in all the samples mercury we have to generate anyway by either by stannous chloride method or sodium borohydride method. They have to be acidic and we have to add sodium borohydride or SnCl2 to reduce mercury, and then we are passing nitrogen to bubble the to drive out the mercury vapor. So, if there is silver, then SnCl2 stannous chloride reduction method, if you are employing for the determination of mercury, the interference level will be 0.005 ppm or weight percent. And then same thing is true even with NaBH4 reduction, and then arsenic in stannous chloride it is about 10% of the mercury. Okay. So, if you are determining about 1 ppb, 0.1 ppb of arsenic can interfere in the reaction, that is reduction of mercury to vapor. Same thing is but with NaBH4 reduction, slightly alkaline conditions, it is 0.25. So, always we say that NaBH4 reduction is preferable compared to stannous chloride reduction, but 90% of the analysis were being conducted up to 1990s using stannous chloride. Even now lot of people do that, but the switching over to NaBH4 is always preferable. Sodium borohydride tablets cost around 800 to 1000 rupees per 100 gram, whereas stannous chloride is much more cheaper. So, because of that reason also people prefer stannous chloride only because of the cost. Now, there are other elements which I have listed here. One is bismuth, that is about 10% of mercury. Copper is also around 10. Iodine is, you should be very careful because 0.003% mercury forms an iodide complex HgI, HgI2, Hgi3 minus and Hgi4 2 minus. All kinds of possibilities are there with iodine, and therefore, one has to be very careful if there is iodine. And if the iodine is not, it is there, we have to find out a way to get rid of this iodine. Okay. There are very simple methods, because we know that most of the halides can be precipitated as chloride or bromide or iodide whose solubilities are very less. Silver bromide, for example, silver iodide, silver chloride, their solubilities are very less. So, if there is any if you suspect any amount of iodine in the sample, what we do normally, what you should be doing is you have to add a little bit of silver chloride solution, and then so to iodine will precipitate as silver iodide, and then that will not interfere. But again you should be very careful because the quantity of iodine is very less. Similarly, antimony 1 ppm or 1% of weight per 1 weight percent of mercury interferes. In stannous chloride this is 2.5, selenium is 0.005, as bad as iodine, and on the other side in sodium borohydride reduction it is 0.5. So, if I ask you to compare the two methods, the method what you choose should be sodium borohydride if both are available. So, sodium borohydride method has gained wide popularity in the determination of mercury. So, then there are process interferences. This I have already told you: gold, platinum, rhodium, ruthenium, etc. They interfere in the determination of mercury when present at 1 gram per liter of the solution. Okay, that is 1 ppm. That is no, not 1 ppm, 1 gram per liter is 1 milligram per ml, yes, that is 1 ppm. So, around 1 ppm levels all these noble metals, gold, silver, platinum, rhodium, ruthenium, all these things interfere in the, if they are present in the analyte solutions. So, this is due to the reduction of these metals and subsequent amalgamation with mercury. I think I have explained to you enough regarding the amalgamation problem with mercury. If any of these metals are around, you should be always expecting some sort of amalgamation. Similarly, copper and silver. Silver interference can be eliminated. We can eliminate, I had already told you that if we add bromides, potassium bromide or sodium bromide, it will form silver bromide, and whereas mercury remains in solution as the HgBr42 minus. Okay. So, same thing is true with respect to other element, that is copper and silver. They also form iodides, and you have to convert them into a least soluble salt with respect to bromide, with respect to mercury. So, iodine interferences is noticeable when the sample is treated with nitric acid. For example, if you want to determine iodine in seawater where there are seaweeds, then they do have they do concentrate iodine as iodide, and whenever you want to determine in organic substances, it is important that we oxidize the organic substance with nitric acid to convert it into inorganic salt solution and then analyze. So, use of nitric acid is very common in almost all chemical analysis of real samples. For example, in seaweed, in food, in agriculture, in plants, materials, etc., nitric acid is always used for the dissolution of the sample. Similarly, sometimes hydroxylamine hydrochloride, it is added to reduce permanganate. Normally, it has a substantial influence on mercury at higher concentrations. So, you have to be very careful if there is permanganate and hydroxylamine hydrochloride, because in this case mercury is not liberated at all. So, you may conclude that mercury may not be there, whereas it could be there in the sample. Okay. Then there are other organic compounds like sulfhydryl groups. These are present in amino acids. So, if you want to determine mercury in the body fluids, amino acids may be there with sulfhydryl groups, and they interfere when the sample is not completely ashed. The treatment of the sample with nitric acid is called ashing, and we also add a little bit of magnesium and other things during ashing process. The details of analysis you can find out from the textbooks or prescribed AOAC methods, Association of Analytical Chemists. They produce a number of monographs and other literature which will give you typical procedures for the determination of for ashing and other aspects of analytical chemistry. So, organometallic compounds, quite often they are volatilized and only partially reduced by sodium borohydride. Sodium borohydride works only for inorganic compounds, not organic compounds. So, but in that case you should go for stannous chloride method. So, organometallic compounds are volatilized, but only slightly partially reduced, but the sensitivity, therefore, the sensitivity of the determination decreases, and the order of decrease of the absorbance reading for inorganic mercury is very high, methyl mercury it is lower compared to inorganic mercury, methyl mercury is lower, and if it is phenyl mercury then it is still lower. Okay. So, if I do the determination of mercury, I use 700 degrees or 1000 degrees, then there is no problem. That is because I have already told you that most of the mercury liberated from the environment goes to a gold foil on which mercury deposits and then amalgam is formed. This amalgam decomposes above 500 degrees or even sometimes even 350 degrees centigrade, you can collect your mercury. In fact, earlier most of the jewelers used to collect small quantities of gold using mercury, forming mercury amalgam and then evaporating the mercury and then collect the gold, which is having higher economic value. So, they used to generate about 600-700 degrees centigrade in the normal kilns, jewelers kilns, but in atomic absorption, if I use 700 degrees centigrade, the sensitivity of methyl mercury, phenyl mercury and inorganic mercury, all of them would be essentially same. But if you use lower temperature, inorganic mercury will give you higher reading compared to methyl mercury, and methyl mercury will give you higher reading than phenyl mercury owing to the decomposition potential of these compounds. Sometimes there may be other elements in the vapor, they may cause poisoning of the gold gauze. Platinum poisoning we are all quite aware, because platinum can form sulfur, hydrogen sulfide can get deposited on platinum and forming platinum sulfide, and then it will the top surface may not be available for amalgamation at all. So, poisoning of the gold gauze by other gases causes incomplete amalgamation. So, frequent reconditioning of the gold gauze is necessary. How do we increase how do we recondition the gold? That is very simple. All you have to do is take out the gold piece, heat it to around 1000 degrees centigrade, and then gold piece is ready for action once again. It is a very simple process, but we should be aware of the complication. That is why I am suggesting that the gold, we have to why people use gold is because gold is least resistant to poisoning. Even though we have written here, there may be other gases that cause incomplete amalgam, surface changes. Platinum and palladium are the most prone to poisoning, but gold also to some extent can happen, because gold can and does form sulfur compounds on the surface. So, frequent reconditioning of the gold gauge is necessary, and you should be doing it if you want to determine gold in number of samples over a period of time. So, if you are regularly doing gold, we say, why do not you recondition the gold piece, put it in the flame and see that most of the sulfur is gone, or simply heat it to 1000 degrees, do not make any measurement, but put it back and then do the analytical determination of the gold. Okay. Now, that is all I wanted to tell you about the mercury determination. So far we have discussed the hydride generation technique as a modular attachment, and also we have discussed cold vapor mercury as an attachment. In cold vapor mercury, what we need is only a small ultraviolet lamp with a small filter, which will give you a 253 nanometer wavelength, and you can determine the mercury in as a modular attachment. So, nowadays there are some dedicated instruments available for the determination of mercury by cold vapor method. You do not need an atomic absorption at all. So, but whenever you buy an atomic absorption, it makes sense to buy cold vapor mercury modular attachment also. Same thing is true with respect to hydride generation. Now, I want to introduce you to another technique, that is flame atomic emission spectrometry. Now, you may be wondering why I am teaching you flame atomic emission spectrometry, whereas we are talking about flame atomic absorption spectrometry. And the reason is some elements can be determined by flame atomic emission rather than flame atomic absorption. But the possibility of using the same optics, same instrument as atomic absorption makes the flame atomic emission also possible for the determination of some elements. What are those elements? I think most of you already know about it, that is lithium, sodium, potassium, etc. These are alkali metals, and there are alkaline earth metals, that is calcium, strontium, barium, etc. So, before I proceed, I want to simply tell you that atomic absorption instrument can be used as an emission spectrometer, atomic emission spectrometer for some elements, okay, only alkali and alkaline earth metals, but the possibility of using atomic absorption instrument as an emission spectrometer is quite there. Just at the flick of a button, you can change from absorption to emission, emission to absorption. So, there is a possibility that whenever you buy an atomic absorption instrument, the instrument will have a switch which tells you whether you would like to do atomic absorption or atomic emission. Any one of these two you can measure. That is why we should know a little bit about atomic emission spectrometry, rather flame atomic emission spectrometry. That is why we want to discuss flame atomic emission spectrometry. There is not much to discuss except to recapitulate some of the things what we have said earlier. So, thermal excitation of the atoms as depicted by this equation, I think all of you are familiar with this equation, that is Nj by N0 is equal to Pj by P0 into e to the power of minus Ej by Kt. This is the number of atoms. If you, for your convenience, I am telling you that Nj represents the number of atoms in the excited state, number of atoms in the ground state, Pj is the probability function of the excited state, P0 is the probability function of the ground state, E is the you know what is E, and Ej is the energy difference, and Kt, K is known as Boltzmann constant, T is the temperature. This equation we have discussed earlier in the theoretical aspects of atomic emission. So, this equation has been used to demonstrate the lower sensitivity of flame atomic absorption, correct. So, the ratio of the non-excited atoms is always more unfavorable in the short wavelength range of the spectrum than the long wavelength range. What we are essentially saying here is at any temperature, the number of atoms in the ground state are more than the number of atoms in the excited state. That is the bottom line, and I have written the same thing in a textbook style, that is the ratio of the non-excited atoms is more unfavorable in the short wavelength range of the spectrum than in the long wavelength range. That means the atomic emission occurs in the long wavelength range, that is above 500-600 range, not in the UV or visible range. Of course, it is visible range, but not in the UV definitely. Okay. So, I had shown you this figure, this table also. At the as we increase the temperature, if the temperature is low, then the concentration of the atoms in the excited state and ground state would be different. But if I increase the temperature from 2000 to 3000, 3000 to 4000, the concentration of the atoms would be more. Now, you can look at this table. This table I have shown you earlier also, and what we want to say at this point of time is, as the hottest flame temperature of around 4000 degrees, the population of the atoms is still very small. They are all in the range of -2 to -3. That means 1 out of 100, 1 out of 1000, 1 out of 10,000, and if it is zinc, it is 1 out of 1 million. Okay. So, but the elements concentration, that is atom concentration, I have given this table, I have shown you earlier. Okay. And this cesium, the resonance line is 852, that is nanometer, that is in the visible range, and the energy required is 1.46, and at 2000 concentration of the atoms is 1 in 10, 4 in 10,000, at 3000 it is 7 in 1000, and at 4000 2 in 100. That means only 2 atoms are in the excited state, 2.98, you can say almost 3. Only 3 atoms are in the excited state compared to 100 atoms. Out of 100, only 3 will be in the excited state. Same thing is true with sodium. Its emission line is 589, and then the electron volt energy required to excite is 2.11. At 2000 it is about 10 atoms in 1 million, and 3000 it is about 6 in 10,000, and at 4000 it is about 4 atoms in 1000 atoms in the ground state. Similarly, you can read the other numbers, and you can see that as we pass through alkaline earth metals, iron, cobalt, magnesium, zinc, etc., they are all in millions, that is few atoms per million. So, that is not very convenient for us, but these numbers can be very significant, as we will see now. So, the atomic concentration I have plotted here, Nj by N0, this is the wavelength, and for cesium it is highest, potassium is lowest, sodium is still lower, strontium, etc., but concentration of atoms like these zinc and other things, they are all in the range of 10 raised to minus 10 range, that is Nj by N0. It is not the total number of atoms, but it is the ratio. So, this figure is very convenient to determine which sort of elements we can determine by flame atomic emission. So, what we want to say at this point of time is that it is not correct to state that atomic absorption is always more sensitive than atomic emission. That is wrong, because the number of excited atoms is always smaller than the number of atoms in the ground state. That is what we have been saying all the while. In flame atomic emission, apart from the Nj, that is the number of atoms in the excited state, the lifetime of the excited state is also more important. So, assume that at any time 4 atoms are in the excited state, but if the excited state remains in the flame for longer time, then the atomic emission can occur very easily. So, the lifetime of the excited atoms is also more important during atomic emission. So, experience has shown that atomic absorption is more sensitive than AES only when the excitation potential is more than 3.5 electron volts. Okay. With lower potentials, flame AES atomic emission is usually more sensitive. So, again as I was telling you, atomic emission and atomic absorption are complementary to each other, which can be measured with the same instrument with the flick of a button. So, majority of the commercial atomic absorption spectrometers nowadays permit flame emission measurement also. So, this is what I have been telling you, but nowadays the flame atomic emission spectrometers are available independently also. They cost very less, approximately about 50 to 60,000 rupees for the data for sodium, potassium, lithium, etc. They are known as flame atomic emission spectrometers, but because we are studying atomic absorption, we will study a little bit more about the flame atomic emission also. We will continue our discussion.